Hi, my name is Zhou Xin. This is my Data 605 final project to begin. I'm start with loading a bunch of library we are going to use. To save the time, I load a function to automatically check if the library are installed. Start with the problem. Here we are going to make sure we generate the same random number by defining the C, and we will then define n. N should be greater or equal to 6. We choose 10,000 here to demonstrate. We further generate a random variable x which has 10,000 random uniform numbers from 1 to n, our case from 1 to 10,000. And given the equation above, we generate the mu and sigma first using sum of n plus 1 over 2. After that, we generate random variable y that has 10,000 random normal numbers with a mean of mu and also the standard deviation of sigma, and again they follow the mu equals to sigma equal to sum of n plus 1 over 2. We will then generate the median and first quartile for y for the next question. And then we are using those variables to generate those probabilities, and the result is pretty straightforward. So as you can see that the probability of variable big X larger than it is median, or variable small x larger than the first quartile of the big Y variable is 59.38%. And for B, the probability of variable big X larger than it is median, and at the same time variable big Y larger than it is first quartile is 38.08%. And for the C, the probability of variable x smaller than it is median, or variable small x larger than the first quartile of the big Y variable is 59.76%. Next, we are going to check the probability of big X greater than small x and big Y greater than small y is equal to probability of big X greater than small x times probability of big Y greater than small y by building a table and evaluating the marginal and the joint probability. So from this table, we can see that we have probability of big X greater than small x, big Y greater than small y is equal to 0.3808, and then the probability of big X greater than small x times probability of big Y greater than small y is equal to 0.3867, and they are obviously not the same. And here, when we try to compare proportion of category outcome according to different independent groups, we can consider several statistical tests such as the chi-square test, Fisher exact test, or z-test. The chi-square test and the Fisher exact test can assess for independence between two variables when the comparing groups are independent and not correlated. The chi-square test apply approximation assuming the sample is large, while the Fisher exact test runs the exact procedure, especially for small size sample. Since we have 10,000 samples here, chi-square test is more appropriate. And here we're going to have the null hypothesis and alternative hypothesis to check their association. The chi-square test is used to compare the distribution of a categorical variable and in a sample or a group with the distribution in another one. If the distribution of the category variable is not much different over different groups, we can conclude the distribution of the category variable is not related to the variable of a group. Or we can just simply say the categorical variable and group are independent. After running those functions, we will get a p-value of 0.008. So the generated p-value from chi-square test we can see is less than 0.05. As a result, we fail to reject our null hypothesis. And for the Fisher-exact test is practically applied only in analysis of small sample, but actually it is valid for all sample size, while the chi-square test relying on approximation. Fisher-exact test is one of the exact tests, especially when more than 20% of cells have expected frequency less than 5. We need to use Fisher's exact test because applying approximation method is inadequate. Fisher exact test assesses the null hypothesis of independence applying hypergeometric distribution of the numbers in the cell of the table. So we can see our p-value stay the same using the Fisher exact test, and therefore we do not reject null hypothesis. Here we go into the problem 2. First I'm downloading this data from the Kaggle website and then putting my working directory and import it into R. Then I'm using the encoder and getting encoder variable data type and the observation just by using grams. Here is the summary. We will also have a look into the summary report of the training data set. The data in the training data set we can see contain the 1,460 rows and the 81 columns. Among them exists quite some missing data entries. I will do the data cleaning later. According to the data description.txt on the Kaggle website, and my some common sense in the real estate market, the most relevant independent variable could be lot area, total basement square per foot, the first floor square per foot. Of course, there are more factors influence the sale price of property, but for checking the correlation, we will just take this upper mentioned variable and check their correlations. From the plot here, we can see there's a positive correlation between our independent variables. The dependent variable sale price can be identified. We use these same variables and visualize real program. Then the correlation are high between some variables, but we won't do anything about it since the aim of this article is to predict and not to exploratory data analysis. This will most likely result in model fitting, but more on that later. The hypothesis testing will test the correlation between each pair set of variables as 0 and provide an 80% confidence interval. We will use chi-square correlation test to determine them. Here we have the null and the alternative hypothesis to check their correlations. We can see each test deliver a p-value way smaller than the significance level, so we reject our low hypothesis. So we can conclude that there's no strong correlation between those three variables and a dependent variable. So family errors using sigma procedure is 0.488, which is very high considering we only run these three tests. The reason for that is our alpha is 0.2. If we change it to 0.001, we will have a very low family-wise error, but it should not be worried since our p-value are very small. Now we will still be significant even if we use a 99% significance level. The linear algebra and the correlation. We will calculate the precision matrix by inverting the correlation matrix. So we noticed that some correlation among these three variables are sales price, especially between total basement scope of food and the sales price. So multiply the correlation matrix by the precision matrix, then multiply precision matrix by correlation matrix. We can see multiply the correlation matrix by the precision matrix and then multiply the precision matrix by correlation produce the same result. Then I'm going to conduct an aerial decomposition of the matrix. I will get this result matrix as following. For the explanation distribution, we choose the ground leaf area above as our selected variable, since in most of the case it is one of the most important factor buyer will consider when purchasing a property. Here we have the 5th and 95% percentile. The estimated 5th percentile is 77.43 and 95 percentile is 4539.92. Here, and the 95% confidence interval from the empirical data assuming normality is between 0.9487 and 1.05. The 5th percentile of the data is 848 and the 95th percentile of the data is 2466. We have to format the data before fitting. Here we are advocate to use multiple regression model. We will use a log change model based on hedonic price models. Here we are checking for the NA's data, and then we're doing some data cleaning, checking the class of each column is numeric. Then we're going to train the model using linear model. The R package code is deployed here for the modeling process. We will start with simple linear model. However, a random forest proposed would be nice to compare if it was allowed. Now we will investigate the attribute of linear models. For linear model object, we will create above the final model is simply a multiple linear regression using the full input data set. Then we'll find out the R-square of the linear model. We see that overall R-square based on the data is just 0.8928. This is the unrealistic R-square. It is worth repeating. This is a R-square from model using all the data. When we want instead is the R-square based on applying our model to new data, which is gray, what we get with resampling. In order to see the realistic R-square based on resampling, we can look directly at the chain object. Here is the brief summary of the resampling in the chain object. We can see that in this case, the resampling R-square is lower than unrealistic R-square we saw from the final model. This data set is large, so the difference between unrealistic and realistic R-square is lower than it would likely to be with a smaller dataset. Although a lower R-square can be disappointing, it is a more defensible and a realistic measure of our model is likely performed on new data. Now I'm going to use tenfold cross-validation as a comparison since the dataset is fairly large. The cross-validation produces a model with similar RMSE and R-square that is not satisfying. So here we will use tenfold cross-validation 5 times. Here we run automate stepwise regression and look at the resampling results. Note that there's no tuning parameter, so the final result table has just one row. Next, we can make a residual plot or residual histogram to be more precise. Here we expect to see something approximately normally distributed. So overall, the sample linear model with cross-validation, after all, the stepwise model performs similarly, but of course, due to the limitation of the computation power, we only implemented a straightforward stepwise model. If that condition was eliminated, the performance of model could be different. We will use the stepwise regression model for its slightly better performance, judging by RMSE, R-square, and MAE. Since it is a log change model, we will then scale the output. And after that, I output my result into the submission CSV with ID and sales price and upload it to the cargo.com. And here's my score in the cargo.com. Thanks for watching.